Okay. So this problem was deceptively difficult. But number 21, it is asking two mass points of mass m1 and m2 are connected by a string passing through a hole in a smooth table so that m1 rests on the table surface and m2 hangs suspended. Then it's saying that M2 can only move in a vertical line, up and down. What are the generalized coordinates for the system? And then we're going to write the Lagrange equation and then discuss the physical significance that that would have. And then we're going to reduce the problem to a single second order differential equation and obtain a first integral of the equation and then ask what the significance of that is. Okay, so to start off, let's draw it. At first, I was thinking that it was something like this, where it's on the corner of a table, like a simple physics problem, but it's a little bit more complicated than that. So you have a table top like this, and you have a hole, you have your string, and this is your M1, and then this is allowed to move in a radial fashion. And down here is where your M2 hangs. And so we automatically can start to measure some things. So your M1, the position of this M1 is going to be based on polar coordinates. There's a phi here, or not a phi, a theta, excuse me, and you have an R. R is going to be the length from the hole to M1. And then down here we'll have like a minus, like we'll just see this as the x, y, z plane, and this is going to be minus z. That's going to be your minus z direction. And then so right now we can already see that minus z plus r is a constant number. So we'll just write that. These dang suggestions. Off. Go away. Okay. It's a constant number. And then we know also in polar coordinates that our x1 or our x value is r cosine theta, and then our y value is r sine theta. And so we have our generalized coordinate systems already. So we have r, theta, we also have the z. So we can solve for z. So we have z equals r minus this constant. So we'll circle these. And so if we're going to be doing Lagrangian stuff, we need our kinetic energy, which is 1/2 m2 z dot squared plus 1/2 m1 x dot squared plus y dot squared. Okay, and this is the potential energy and kinetic energy and polar coordinates are known, but we'll just go ahead and sort of derive them here, so it's not too bad. X dot is, we have chain rule, r dot cosine theta minus r theta dot sine theta. It's just the product rule, and then y dot is going to be r dot sine theta plus r theta dot cosine theta. And then we have to square these, which x dot squared is r dot cosine squared theta plus r squared, the other term, theta dot squared sine squared theta plus the term in the middle, which is minus 2 r dot r theta dot cosine theta sine theta. Now we'll do our y dot. Y dot squared is r dot squared sine squared theta plus r squared theta dot squared cosine squared theta plus 2r dot r theta dot cosine theta sine theta. We can see right away when we're adding these together, these are going to go away. And then you can see already that these are going to combine, and these are going to combine, and when you combine like terms, you get x dot squared plus y dot squared equal to r dot squared plus r squared theta dot squared. And that is known, that's a known result, but we'll just do that anyway. So then our t goes to 1/2 m2 one second here. Yeah, m2 r dot squared plus 1/2 m1 r dot squared plus r squared theta dot squared. Okay. Yeah, because the velocity of z is dependent on r, so that's why we put that there. But our u, though, is going to be m2gr minus m2gc. This was our constant from up here. Now, we can actually do something about this. We can, but we'll, there's a way to do this where you let c become r, where it's right in the middle of the table, and it sort of simplifies things, but we're going to wait a second to do that. These are our two coordinates. And so to write our Lagrange out, let's change colors. Get L equals 1/2 m2 r dot squared plus 1/2 m1 r dot squared plus r squared theta dot squared minus m2gr plus m2gc, this constant, and then that is equal to 1/2, and we'll just distribute this term and then combine them. So we 1/2 m1 plus m2, and then r dot squared plus 1/2 m1 r squared theta dot squared minus m2gr plus m2gc. Okay, so this is our Lagrangian. And let's start with theta first, because there's something important that comes from this, and that is if you do this, the partial derivative of the Lagrangian with respect to theta is there are no thetas, so it's 0. And that means that the time derivative of the theta dot, so let's do theta dot first. Okay. I'm getting ahead of myself. So the partial of the Lagrangian with respect to theta dot, we'll just pull it from right up here. Looks like there's only one term, and that equals 2 over 2, which is 1. So just m1 r squared theta dot. And this right here is very, this is a big thing. So this is our angular momentum, and if the time derivative of this is 0, like it is in this Euler-Lagrange equation, then that means the time derivative of, we'll just put little l, is 0. that means that the angular momentum is conserved in this system. So we're going to put this equals L. This is very important. We're going to hang on to this for later. So that's just something to know, because this is omega, right? So this is the velocity, the angular velocity. So mr squared times the angular velocity, that is the angular momentum. There we go. So now let's go down and do r. So we'll do this with respect to r. This is going to be m1r theta dot squared minus m2g. And then if we do the del L with respect to r dot, that's going to be just m1 plus m2 r dot. You can write this as capital M if you want total mass, but it doesn't matter. We'll just keep them separate. And then d over dt of this is just m1 plus m2 r double dot. Beautiful. And so we get this equation m1 plus m2 r double dot minus m1 r theta dot squared minus m2g equals 0. All right, so we can actually rewrite this. Oh wait, hold on. Did I get a negative wrong? So it's minus this. So yeah, so that one would be plus this minus that. Okay, now we have it correct. All right, so we can rewrite this where if you solve for, using this equation here, if you solve for theta dot, then you get L over mr squared. And so we can, since this is constant, since the angular momentum is conserved, that means we can replace everything in our Lagrangian or Euler-Lagrange equation with L. When you do that, you get m1 plus m2 r double dot minus L squared over m1 r cubed plus m2g equals 0. So this is our new combined second differential equation. Now if you take the first time derivative of this, like the book is asking us to do, and m1 plus m2 r dot squared plus L squared over m1 r cubed minus m2gr, then you end up getting m1 plus m2 r dot r double dot minus L squared over mr, oh sorry, this is squared. Did I cube it too early? Okay. R cubed r dot minus m2g r dot equals 0. And so you get m1 plus m2 r double dot minus L squared over m1 r cubed minus m2g equals 0. And this is our Lagrangian. So taking the Euler-Lagrange equations and doing a first time derivative of that gives you the original Lagrangian. And what that tells you is that the Lagrangian is constant, which means that the system is closed energy is conserved. And linear and angular momentum are conserved. And that's it.